talks in this session. The first one is a new generic transform from multi-round interactive proof to NISIC by Pierre Allen Falk, Adela Gorgescu, Chen Quan, Adeline Langlois, and Wei Kwai Wen. Sorry for the pronunciation, and Chen will present the paper. Over to you.
Okay, thanks for the introduction. Hello, everyone. So I will present to you our work about a new generic transform from multi-round interactive proof to NISIC. This presentation were composed by mainly 4 parts. So firstly, I will give a brief introduction of all notations just to fix the notations. Then I will compare our transform to the existing transforms, mainly about Fine-Jamir and our starting point, which is a TCC 16 paper proposed by CPSV. Then we will, as CPSV paper is our starting point, I will give a quick introduction of their main technique, and then I will introduce our new technique and new all-proof technique and our new transform. Then we will conclude this talk. So let's first go to the introduction. So first of all, our work is about transform from multi-round interactive proof to NISIC. So I will first give some notations about the multi-round interactive proofs. So basically, it's an interactive protocol between Alice and Bob. The goal is to prove a statement X is in the language L with a witness W. So the main goal for Alice is to prove the statement X is in the language without leaking the witness W. So the first property of such protocol is the correctness. So basically, it means honestly generated proof should be verifiable. Then the soundness, meaning that if the statement is not in the language, it is computationally hard to produce a valid proof. There are some details for the soundness. I will go through the details in the next slide. And then we call, for the interactive proof, we call the honest verifier knowledge, meaning that the transcript does not leak information more than the fact that X is in the language. Or more formally, there exists a simulator with all the challenges. We can simulate a valid transcript. So in this work, we mainly consider 2 types of soundness. The first is called round-by-round soundness. So the original definition defined a doomed set, and there are some details of this definition. But in our work, the important thing to mention is that this round-by-round soundness, it can be applied directly from the negligible soundness. However, there's some security loss by such transform. The second soundness we consider is the optimal soundness, meaning that there exists I such that given a transcript until the round I, there are only very few answerable challenges. The thing to need to mention for the optimal soundness is that it is a generalization of spatial soundness. So basically our transform works both for round-by-round soundness and optimal soundness. However, since round-by-round soundness can be implied by negligible soundness, and optimal soundness is a stronger property, and if we apply our transform on round-by-round soundness, we have a bigger security loss. So let's talk about our contribution. We summarize our contribution. We compare our work with the famous Fine-Jamir transform and CSPV transform proposed by in TCC 16. So we compare this 3 transform in 3 dimensions. So first is that are they support multi-round interactive proof? The second and the third property is about the soundness and the zero knowledge property. So for the Fine-Jamir transform, they actually support multi-round PCIPs. But for the CPSV transform, they doesn't support PCIP. However, the CPSV transform has some advantage has some advantage over Weishaupt transform in the sense that their zero knowledge property is proved in the standard model instead of random oracle model. And the soundness property of the CPSV paper can be proved in the non-programmable random oracle model. So our work basically combined the advantage of both transform in the sense that we support multi-round PCIPs, and we also have this zero knowledge in the standard model and the soundness in the non-programmable random oracle model. So the first thing to mention is that the random oracle versus non-programmable random oracle. So non-programmable random oracle is a weaker model, and so it is theoretically interesting. And moreover, I need to emphasize that for the zero knowledge property, our transform and the CPSV transform, they are both have zero knowledge in the standard model. They can since the zero knowledge property is usually used to provide privacy in the high level protocols, our transform and CPSV transform can somehow provide long-term privacy for high level protocols like privacy in e-voting and etc. The third point I want to mention is that the importance of multi-round. So nowadays, there are some bulletproofs and new lattice-based exact proofs. They all benefit from the fact that there are more rounds than just three passes, and they can benefit from the multi-round to have more efficient constructions. So next, I will give a brief description of the CPSV transform. And I will explain why they cannot extend to multi-round and why the intuition of our work. So our starting point is a CPSV paper. So their goal is to transform from Sigma protocol to NIZK with a proof language error. The high-level construction is relatively simple. So basically, the idea is to use another NP hard membership problem, L prime. Then the common reference string of the zero knowledge proof is an X prime, which is not in the language L prime. And the construction is that the final proof, it consists of a NIZK proof of the form X in the language L or X prime in the language L prime. So just to give a brief proof intuition of their transform, first for the soundness, since X prime is not in the language L prime, the prover needs to provide a correct proof for X in the language L. And for the zero knowledge, we can switch the CRS with X prime in the L prime. Since L prime is a NP hard membership problem, this switch is computationally indistinguishable. Then the simulator can prove with this new witness W prime. So the main difficulty for multi-round PCIP is that the core part of CPSV is an all proof of Sigma protocols. However, the existing all proof technique cannot be used on multi-round PCIP. The existing all proof technique, basically, there are two existing all proof techniques. The first is a parallel all proof proposed by Kramer and et al. In Crypto 94, and a sequential all proof originally proposed by Abe et al. In Asia Crypto 02. So I will briefly explain why they are not, why they cannot extend to multi-round proofs. So for the CTS all proof, we can see that here we want to combine all two Sigma protocols. The proof is of the form like R0, R1, H0, H1, and S0, S1, with the special fact that H0 so H1 is equal to the hash of the first round commitments. So the adversary can freely choose H0 or H1. So if the adversary can choose H0, then he can simulate the proof of the side 0. If he can freely choose H1, then he can freely simulate the proof of pi 1 without without W1. However, why this all proof cannot work for multi-round? We give a counterexample here. Here we extend both proof into five rounds by adding some dummy rounds. In the left side, we add this as at the third and fourth path, and on the right side we add at the first and the second path. So they are all dummy rounds, meaning that all messages are just uniformly random messages and ignored by the proof protocol. So if we use the CDS or proof, we can see that the adversary can freely choose both H0 and H1. Then he can basically simulate the left side and right side without any witness. So this is directly break the protocol. The second all proof technique is called AOS, proposed by AOS in the Asia Crypto 02. However, they have this exact same form of proof with the special fact that H0 equals to the hash of the opposite side. So the adversary can freely choose H0 or H1 depending on the order. So there's an order execution order between the left side and the right side. However, if we extend this technique to multi-round, the adversary cannot choose any order between left and right. So syntactically, the sequential all proof cannot extend to multi-round. So next, I will explain our new all proof technique, and then give our new transform. So the intuition of our new all proof is that first we need to combine all the challenges of one side together. This is somehow comes from the parallel all proof. And second is that we kind of need to separate the challenges from each side. So let's start with our first attempt. So we use the idea from the parallel all proof. We combine all the challenges of the same side together by an offset fixed in the hash input, meaning that we give an offset AB, which is a set of A1B to A and B, and the first I round commitments R1B until RIB. The challenges is of the form H of the first round of commitments XOR the offset AI0. So in this way, once we have fixed the offset at the very beginning, the challenges is totally fixed by the first round's commitments. However, this doesn't directly work. We need also borrow idea from the sequential all proof. The sequential all proof, we kind of need to add the order between the left side and the right side. Then we, in order to fix the set A0 and A1, we add this offset in the opposite side of the hash function. Then I will quickly explain how can we generate a proof with only WB in such case. So we first generate a random offset AB. Then we use the HVZK property, the zero knowledge property, to simulate pi IB with all this transcript, including the commitments and the challenges. Then we can compute the AI1 minus B with this exact form of hash of the commitments and the offset AB XOR with the challenges HI1 minus B. Then using the offset A1 minus B, we can using the offset a b and a1 minus b, we can compute the pi b using the WB honestly. So finally, I will give this is the intuition of our transform. I need to emphasize some security and the theorem about our transform. So in the classical setting, our transform is in NP room and is suitable for optimal sound, and which is a generalization of spatial soundness, and the round-by-round soundness, which is which can be implied by the negligible soundness. And in the quantum setting, we have the Q-room-based proof with security loss QH to the 4 instead of QH to the 2n, with QH is the number of hash query and n equals to the number of rounds. So for the conclusion, our first contribution is the first all-proof technique for multi-round PCIP protocols. And secondly, we provide first generic transform from multi-round PCIP to NISIC with soundness in the NP room model and zero knowledge in the standard model. And also, our transform is the first transform in Q room with security loss QH to the 4 instead of QH to the 2n. So I didn't present the proof detail of the Q room proof. The detail is in the paper. So somehow for the open problem, the main open problem is that the proof in the Q room require programmability. So does there exist a transform in Q room without programmability? This is left as a future research direction of our work. That's all for my presentation. Thank you very much.
Thanks for the talk. So any questions for Chen? Yep.
Thank you for a nice talk. Just regarding this final open problem, what is the motivation for not wanting programmability? Is it just because it's philosophically nicer, or are you hoping that you might get something tighter?
The first, yeah, the answer of your question is first is theoretically interesting because we want to because random oracle theoretically is an impossible. There are some impossibility results regarding to the random oracle model. So we always want to use a weaker model than the random oracle model. So like this is the motivation, and also since we have this zero knowledge property in the standard model, so it somehow provides long-term privacy is also another motivation.
Okay, thank you.
Any more questions? Okay, let's thank the speaker again. So the next paper is 196. Okay, so the second talk will be on fine-grained verifier NISIC and its application, presented by Xiangyu Liu, Shengli Liu, Shuai Han, and Dao Gu, and Xiangyu will give the talk.
Okay, thank you. Hi, good afternoon. I'm Xiangyu Liu from Purdue University, and I'm here again to give the talk, Fine-Grained Verifier NISC and its applications. I'm sorry, the laser. Excuse me, is there a laser? Oh, I saw it. Thank you. And it's a joint work with Shengli Liu, Shuai Han, Dao Gu in Shanghai Jiao Tong University. Well, we may start from NISC, non-interactive zero-knowledge proofs or arguments, and I guess most of us are very familiar with it. In NISC, we define a language L by a relation R, and we say an instance C belongs to L if and only if there exists a witness W such that R3W is equal to 1. Well, NISC has many applications as shown in this figure. The prover now it can with C and witness W, it can generate proof pi and send it to the verifier V. While the verifier V, with the help of CRS, common reference string, and it can evoke the verifier algorithm to output a bit 1 or 0 to decide whether C belongs to the language L. And NISC has two variants, and namely QA NISC and DV NISC. QA NISC, quasi-adaptive NISC, is a specific NISC where CRS depends on specific languages. And similar to regular NISC, QA NISC supports public verification. That is to verify a proof, we just need the proof, the instance, and the CRS, which is published over the internet. And DV NISC is short for designed verifier, QA NISC. And in DV NISC, not only does the CRS depend on the specific language, but also the verification algorithms additionally tags a secret key SK as input. So due to this reason, DV NISC supports private verification, but usually compared with QA NISC, it has more succinct constructions. However, we will show two examples to see neither QA NISC nor DV NISC has their own shortcomings in the fine-grained verifier setting. Okay, the first example is in the IPFE setting. IPFE means inner product functional encryption. As shown in these slides, we encrypt vector X using MPK, master public key, to obtain a ciphertext CT. And we can also obtain a secret key SKY from the master secret key MSK with another vector Y. And using SKY to decrypt a CT, we can obtain the inner product of X and Y. So that's IPFE setting. That's the syntax of IPFE, and we can see it contains a key generation algorithm. Now, suppose we already have a CPA secure IPFE scheme, and we want to lift it from CPA to CCA. Actually, we want to lift from MCPA to MCCA. Here, M means multi-user and multi-channel setting, and it's a generalization of traditional CPA and CCA security. So a natural idea is to use NISC in the ciphertext. We add a NISC to prove that the ciphertext is well generated, namely the ciphertext is valid. However, how to choose a suitable NISC, we may face the following problems. And if we choose DV NISC, which supports private verification, then how do we deal with key derivations? Since we know in IPFE, we need to derive the different secret keys with respect to different functions Y. So DV NISC cannot support key derivations, so that's a problem. But if we choose QA NISC, which supports public verification, we can just ignore the key generation algorithm and just since we do not need any secret keys to do a verification algorithm. However, it may be overused since in the IPFE setting, we do not need anyone to do the decryption scheme, to do the decryption algorithm, but just those who have the secret key to do the decryption. So QA NISC is okay, but it might be overused. And the second example is fine-grained PKE, public key encryption scheme. Now consider this setting. Suppose Alice, she obtained lots of ciphertexts from the internet. And among these ciphertexts, there might be some invalid ciphertexts, for example, some advertisements or junk emails. So now Alice, she wants to hire an assistant to filter those invalid ciphertexts for her and just pass those valid ciphertexts to Alice. Actually, now Alice wants to assign her check ability to the assistant, while at the same time, she also wants to keep MCCA security holds even against her assistant. We know NISC is a useful tool to design CCA secure encryption schemes. But how to choose a suitable NISC? If we use DV-NISC, which supports private verification, and the same question occurs, so we cannot deal with key derivations. And if we use QA-NISC, then the anonymity of the encryption scheme may be sacrificed, since anywhere on the internet, it can check whether a ciphertext is sent to Alice by just doing a verification algorithm, since the CRS is public and no secret information is needed in the verification algorithm. So there's no anonymity in our protocol or in our algorithm. So that's the question. Okay, from these two examples, we can see that neither DV-NISC or QA-NISC has their own shortcomings. So in this work, we make the following contributions. First, we define a new primitive called fine-grained verifier NISC, or FV-NISC for short. And it supports two verification approaches. First is master verifier, or M-verifier for short, which use MSK as an input. And the second is fine-grained verifier algorithm, or F-verifier algorithm for short. And it uses a derived secret key SKD from the master secret key. Here, D is designed value. It can stand for some IP address or identities and some other things. And we equipped three security properties for FV-NISC: verification soundness, unbounded simulation soundness, or USS for short, and proof pseudorandomness. Well, the first one, verification soundness, requires F-verifier and F-verifier algorithms perform statistically identical, equivalent. So that's the requirement. And unbounded simulation soundness is defined similar as that in DV-NISC or QA-NISC. And it's important for us to prove the CCA security of encryption schemes. And proof pseudorandomness requires that the generated proof of FV-NISC is pseudorandom. And for linear subspace language, we designed two constructions with tight security. And the first one is pairing free, but and the security loss is linear in lambda, the security parameter. And the second one is pairing based, but it has a better security loss. Namely, the security loss is logarithm in lambda. And at last, we show two applications. One application is to construct MCCA secure IPFE, and another application is to design fine-grained verifiable PKE, or FV PKE for short. Okay, now since we already know the definition of FV-NISC, then how to design a FV-NISC scheme? So our start point is the DV-NISC in GHKW16. This slide shows the DV-NISC construction of GHKW16. And the master secret key contains K, a vector, and a series of vectors K hat. And as for the proof, it has two parts, T and U. That's the proof verifier algorithm, and that's the verifier algorithm. Okay, from this slide, we can notice that it has good linearity. That is the proof and the verifier algorithm, they just take linear computation. So due to this property, now we design FVNISC as follows. And our first attempt is to extend MSK from vector to matrix. As highlighted in blue, now MSK contains K and a series of K hats. All of them are matrix. This is designed to let MSK contain more entropy so that it can support K derivation algorithms. But and next we design proof and M verifier algorithm just as those in DVNISC. And next, for delegated value D, which is a vector, how do we design F verifier algorithm? And our idea is as follows. Now, that's the F verifier algorithm. And we can see it actually is just do what M verifier did on the projection of D on this vector. So that's our design of verifier, F verifier. And as for SK, it contains D transpose times K and D transpose times K hat. But this is not enough since we have two problems in this design. The first problem is now M verifier and F verifier, they are not statistically equivalent. Actually, for an adversary, since it knows D, and it's very easy for the adversary to generate proof pi, which may pass F verifier but fails to pass M verifier. So that's the first problem. And for the second problem, MSK is fully exposed after M times K derivation for the linear independent D. So, and we know if the MSK is exposed, then there's no security at all. So how to solve these two problems? Our idea is to introduce a random matrix M. Now we add M of size M times M plus 1 in MSK. And we also modify F verifier as follows. Actually, now F verifier checks the validity of proof U on the projection of D transpose times M. Actually, we can view M as a future matrix, but now how can M solve the above mentioned two problems? For the first problem, now since D transpose times M distributes uniformly, so that is from the adversary's view, M verifier and F verifier algorithm, they perform statistically equivalent. So we solve the first problem. And as for the second problem, now since M is of size M times M plus 1, and even after M times K derivations, now there's still some entropy left in the MSK. So this entropy can help us to give a proof for the soundness of NISC. Okay, now we finish our design of the FVNISC. Okay, but that's just the first construction, and starts from the DVNISC. In this work, AJO plus 19, we can construct another FVNISC scheme, and they share the similar idea, and we may safely omit these slides. Now we will show two applications of our FVNISC. The first application is to construct MCC secure IPFE. Now suppose we already have CPA secure IPFE scheme. Then we just add an FVNISC pi into the ciphertext. And as for key generation, we add secret key SKF from the delegation algorithm. Now, for one thing, since FVNISC it supports key derivation algorithm and is suitable for our IPFE setting. And for the second thing, now the unbounded simulation soundness its property is still hold even after deriving several secret keys out. So MCCA security is guaranteed in IPFE. And that's the first application. And as for the second application, similar now, Alice can now Alice want to assign her checkability to the assistant while keeping the MCCA security at the same time. Now Alice can just derive a secret key to her assistant, and since FVNISC supports key derivation, Alice can do it. And meanwhile, USS still holds after deriving several secret keys, and that means MCC security is guaranteed even against the assistant. So that's the application in fine-grained verifiable PKE or FVPKE for short. Okay, to make a conclusion, in this work, we proposed fine-grained verifier NISC, FVNISC for short, and it supports fine-grained verification algorithms. And we designed two constructions for linear subspace language with tight security. And we show two applications in IPFE and FVPKE. Okay, that's the main idea of this work. And thank you for your time. And that's all. Yes.
Thanks for the talk. Any questions? So I have a question.
Okay, please.
So for the FVNISC, so when you generate the master secret key, do you need to know the language?
Yes, you need to know the language first.
So it's also kind of like quasi-adaptive.
Yes, quasi-adaptive, yes.
And do you know like any formal connections between FVNISC, QNISC, and DVQNISC? Like, do you have any formal implications between these notions?
Sorry, I didn't follow
so-
your question.
So you have this different like flavors of the definitions, right? Like DVNISC, DVQNISC, and now you have this new notion of FVNISC, right?
Yes.
So do you have any formal implications between these two notions, or do you think like FVNISC is stronger than or like the previous notions?
Actually, I think FVNISC lines it's located at the middle of DVNISC and QNISC. From the definition, we can say FVNISC directly implies DVNISC, but towards QNISC, we may need additional cryptographic assumptions or some other methods. Yes.
Okay, thanks.
Okay, thank you.
Any more questions? If not, let's thank the speaker again.
Thank you.
Paper 129. So the next talk will be on zero knowledge arguments for subverted RSA groups. It's by Dimitris Kolonelos, Mary Meller, and Mikhail Volkov, and Dimitris will give the talk.
Good, can you hear me? Okay, can you hear me? Okay. Good. Okay, so yes, I'm Dimitris. I'm going to continue talking about zero knowledge proofs. Of course, we are in the ZK session. So this is a joint work with Mary Mahler and Misha Volkov. And most of the work was done while me and Misha were interns at Ethereum Foundation. Okay, so I want to start my talk by telling a few words about the cryptographic setting that I like, which is the one of hidden order groups, or groups of unknown order. It's the same terminology. So these are groups where presumably computing the order is computationally hard. So from now on, let's say that for the rest of the talk, we are only concerned about multiplicative groups. And let's see what happens if one wants to if one wants to perform an exponentiation over these groups. So the thing is that normally if we want to exponentiate something over a group like g to the x, first we take the exponent, we apply the modular operation, modulo the order of the group element, and then we perform the exponentiation normally. Now, in this case, since we do not know the order of the group, with high probability we do not know the order of the group element on the base, in the base. That's why the only way to perform the exponentiation is by interpreting the element x as an integer element. We are performing the exponentiation over the integers in the exponent. So this gives us a unique capability of treating in the exponent elements over the integers. Computationally, the elements in the exponent are integers. So this is something that, at least to the best of my knowledge, is something that only groups of unknown order offer. For example, in the D-log setting or in the bilinear group setting, we have a finite field. On lattices, we have a polynomial ring, or it depends, or just a ring. It depends. It's always something bounded. Here, our domain, our cryptographic domain, let's say, of our functions are the integers computationally. So this has given rise to many nice cryptographic primitives like accumulators, set membership proofs, range proofs, vector commitments, polynomial commitments and snarks, verifiable delay functions, time lock puzzles, additively homomorphic encryption, and the list is not even exhaustive. Even the next talk is going to be about polynomial commitments from hidden order groups. And I want to denote here, maybe to make a bold statement and say that specifically for accumulators, verifiable delay functions, and additively homomorphic encryption, if we do not care about post-quantum security, then the best candidates that we have to date are from hidden order groups. For example, for additively homomorphic encryption, we don't have any candidate from pairings or the D-log setting. El-Gamal is multiplicatively homomorphic. Okay, so what are these hidden order groups in concrete? We have two prominent examples, RSA groups and class groups. RSA groups, I think, are pretty well known. There's a modulus, which is a product of two primes, and then computing the order of this group that is generated by this modulus is equivalent to factoring n. So this is good news because factoring is a very well-studied assumption in cryptography. On the other hand, we have a structure setup because this n is highly structured. It's a product of two safe primes. Then we have, on the other end, class groups of imaginary quadratic order. The way that they work is much more complicated. It's not the scope of this talk. I'm not even an expert to describe how they work. The good thing is that we know that how to generate them in a transparent way with uniformly random bits. However, cryptanalysis in class groups, it's still behind in comparison to factoring. So here I want to stress out, let's say, an implicit third cryptographic setting, the one of subverted RSA groups, which is a natural setting when the setup, the generation of the RSA modulus is adversarial. We do not assume any trust on the RSA modulus, but we give the generation of this modulus to the adversary. So this is kind of good, but on the other hand, we don't have any guarantee about the structure of the modulus and the underlying group, and we cannot even assume that the adversary does not have the factorization of the modulus. So this work is about zero-knowledge proofs over this highly adversarial, highly malicious setting of subverted RSA groups. So a concrete example of where these subverted RSA groups can appear is in Paillet encryption, which is one of the additive homomorphic encryption schemes that we know. So in Paillet encryption, at the very least, the public key contains an RSA modulus. So it's very easy for the party that is generating their key to subvert this modulus n. Now, of course, one would wonder why would anyone subvert their own public key, right? It's kind of controversial. It's kind of paradoxical. So there is this encrypt under your own key and proof paradigm, in which I'm encrypting a message under my own public key, and then I'm proving something in zero knowledge, a property about the underlying message of the ciphertext. So by subverting my own public key, I am hoping that I can cheat later in the zero knowledge proof. And this encrypt under your own key and proof scenario appears in ceremonies for RSA modulus generation, in threshold DCDSA, and in e-voting, at the very least, the ones that I know. Okay, so a bit more formally, zero knowledge proofs are protocols between two parties, a prover and a verifier. A prover and there is a public instance X, a public instance X, and a public relation R, and the prover wants to show to the verifier that X satisfies a relation R, the relation R, without leaking any information about the witness W. So there are many properties that we assume, one of which is we want this specifically in our case to be a proof or argument of knowledge, in the sense that if the verifier accepts, then the prover should absolutely know a witness, a corresponding witness with respect to X and the relation. Specifically in our case, we consider arguments of knowledge in the sense that in the security game, we assume that the prover is computationally bounded, polynomially bounded. We want zero knowledge, of course. We want, in our case, the proofs to be non-interactive. And also, in our case, we use the designated verifier model that also, I think, was introducing. So this model says that the proof can be verified only by a party that possessing a verification secret key. The proof is designated to a specific verifier. Okay, so concretely in our contributions, we introduce a designated verifier, zero knowledge argument of knowledge, of a pre-image for any additive homomorphism that works over possibly subverted RSA groups. And this homomorphism can be, for example, a group exponentiation, modulo n, or a Payet encryption. Then we extend this to range arguments in the sense that the pre-image that we saw knowledge of, we saw that it also lies in a specific interval. And from a technical point of view, we introduce a new interesting extraction technique for proving that our protocols are knowledge sound. And this technique may be of independent interest. Okay, so as we said, we have an arbitrary modulus n chosen by the prover that can be malicious. We have an additive homomorphism. From now on, let's take the simplest, which is the, let's see if this works, yes, which is the simple exponentiation. There are many approaches that one could take from the literature. Unfortunately, I don't have time to go into depth for all of them. I want to denote that in our case, we go for the sigma protocols. Now, the thing is that sigma protocols do not work quite well in groups of unknown order. There are impossibilities results that are showing that we need to repeat the protocol lambda times in order to have a negligible soundness error, which means that this induces a lambda efficiency overhead in the proof system. Now, for the rest of the solutions, they all have some type of efficiency bottleneck. The objective of this work is somehow to use sigma protocols techniques but avoiding to have these lambda repetitions. So what are sigma protocols? They are maybe the simplest form of zero knowledge proofs. They are three-round protocols between the prover and the verifier. The prover is sending a first randomized message A. The verifier responds with a uniformly random challenge C. And then the prover again sends a third message, normally deterministic, and S. And the verifier is checking for consistency of the first message and the third of the prover with respect to the challenge C. So, okay, this doesn't look quite non-interactive, but we can make it non-interactive via standard fiat, the standard fiat Samir technique. Now, how do we prove knowledge soundness in Sigma protocols? Normally, we want to construct an extractor that extracts a witness if the proof is verified. So this extractor runs the protocol once in order to obtain a first accepting transcript. And then what the extractor does is to rewind back to the first message in order to obtain a second accepting transcript on the same first message. So why do we insist so much on having the same first message? Well, it is because if you observe the verification equation, if we divide the two accepting transcripts, the verification equations of the two accepting transcripts, we can get rid of this first message A, and we can get something of the form G to the S minus S prime equals Y to the C minus C prime. So we are almost there. We want to extract something of the form G. We want to have something of the form G to something equals Y. So we are almost there. We only need to get rid of this C minus C prime. So normally what we would do is to exponentiate with the inverse of C minus C prime. However, this is something that we cannot do in groups of unknown order. Somehow the intuition is that, we said that somehow computationally in the exponent, we are working over the integers. So with high probability, C minus C prime does not have a multiplicative inverse. So the only way to make the protocol sound, to be able to extract a witness, is to set the challenge space to be 0, 1, which has inherently a soundness error 1/2. So that's why we require the lambda repetitions. And this is the gist, let's say, of the impossibility result by Bangerter et al. And Terelius and Widstrom from 2010 and 12, respectively. Here, I want to say that this impossibility result can be somehow circumvented by introducing some structured generators, some structured group elements as a CRS, and taking an assumption over the group. However, in our case, we are not able to take any assumption over the group because this group is subverted. We cannot assume anything about the structure of this group. And we cannot even assume that the prover doesn't know the factorization of this underlying group. So what can we do? Except instead, our approach is to run the extractor until we have M accepting transcripts on the same first message. And then we get M minus 1 equations of the form G to the beta I equals Y to the delta I. And of course, here we need to get rid of these delta i's again. But now the observation is that we can use we are over the integers, but we can use this Bézout's theorem, which says that as long as these delta i's are coprime, then there exist some coefficients, namely the Bézout coefficients, such that the linear combination of these coefficients and the delta i's is equal to 1. And this holds over the integers. So if we have this coprimality, we can use these Bézout coefficients, linearly combine somehow and get rid of the deltas from the right hand side. Now the question is, how can we guarantee that this GCD of the deltas is equal to 1? These delta i's are basically differences of the challenges. The thing is that the prover can be smart and choose the type of challenges to answer so that this GCD is never equal to 1. So for example, the prover can only choose to answer even challenges. And then the GCD is going to be at least 2. So our approach is to partially hide the challenge from the prover by having it being a linear combination of something hidden from the prover and something that is sampled during the protocol. And here comes our core technical contribution, which is our information theoretical lemma, which says that if the challenge is of this form, a linear combination of something hidden and something public that is sampled during the protocol, then for any distribution of B, and for any distribution is very important because it means that the prover cannot does not have any hope by choosing the distribution of B's that will answer. So for any distribution of B, one can obtain a polynomial number of transcripts such that this GCD of the differences of the challenges is equal to 1 with overwhelming probability. Okay, and with this approach that we partially hide the challenge from the prover, we can then use this, let's say, core lemma and the GCD extraction technique that uses the Bézout coefficients in order to extract a witness and get knowledge soundness. Of course, the outstanding question now is how do we hide this hidden, how do we hide this part of the challenge from the prover? And the answer is that here is why we need the designated verifier model. The verifier encrypts this part and puts this ciphertext in the verification public key and encrypts these DIs in with a linearly homomorphic encryption. And then during the protocol, the prover can compute this linear combination of the hidden part with the public part that is sampled during the protocol with by linearly homomorphically combine the ciphertexts. So in the paper, we have, of course, more technical details. We have the range protocol that again works under subverted RSA groups. We have we take care of having malicious and reusable designated verifier keys. And we also have an implementation that shows that everything works pretty much well. So for example, for a parallel range proof, we have a prover of 192 milliseconds, a verifier of 125 milliseconds, and a proof size of about 11 kilobytes. Of course, we want to be upfront and say that the protocol has some limitations. It is in the designated verifier model. It is not publicly verifiable. It has a relatively expensive designated verifier key generation. If we want to allow the verifier to be malicious in the zero knowledge property, and we have polynomial reusability of these designated verifier keys if we allow verification oracle queries to the prover. That's it, more or less. I think I'm out of time. So the summary would be that we introduce protocols over subverted RSA groups. And I think that the most interesting part is that even if you don't really care about the subverted RSA groups, there is an interesting extraction technique that we used that we would be very happy to see it being applied in different contexts. So yeah, that's it from me.
Thanks for the talk. Any questions in the house?
Thanks for the talk. So does the extraction technique work if you in public verifier setting, if you do not assume a subverted group?
So this technique works as long as there is a part that is hidden from the prover. We could not find any other way by having the verifier encrypted. So we tried it. Okay. I mean, I don't know the answer of this. I mean, if you can find a way to hide some information of the challenge from the prover, then it will work. The information theoretical lemma works. This is for sure. Mm-hmm. But the question is, how do you hide this part from the prover?
Okay, thanks.
So I have a quick question. So you considered Sigma protocols and then you convert it to the non-interactive setting using Fate Show Me, right?
Yes.
So so the random oracle is also part of the setup. Do you consider subverted random oracles?
No.
Okay, so the assumption is that the group
yes.
during setup can be subverted, but it's still a
yes.
fine random function.
Yeah. So the group is somehow part of the instance, part of the statement. It's not part of the setup. But the random oracle is part of the setup.
Okay, gotcha. Thanks. Any more questions? Yep.
Just wanted to ask a clarification. So at first you mentioned that impossibility results for having like less than lambda repetition. So in your case, if I understood correctly, like you are, you're bypassing the impossibility using designated verifier, or is there something else that I misunderstood?
So this impossibility result works, first of all, without a trusted setup. In our case, the designated verifier model is kind of a setup. We don't have a CRS, we don't have a trusted CRS, but the impossibility result is for publicly verifiable protocols. So, of course, we are not saying that the impossibility result is wrong. We circumvent it by having a restricted somehow protocol.
Okay, I guess we're out of time. So thanks for the talk again. Uh, 114. So the next talk will be on DU, Transparent Constant Size Polynomial Commitment Scheme. It's by Arasu Arun, Shaya Ganesh, Satya Lokam, Tushar Mopuri, and Sriram Sridhar, and Sriram will give the talk.
Can you hear me? Okay, thanks for the intro. Yeah, this is our work on constructing a transparent constant size polynomial commitment scheme. This is joint work with Arasu, Chaya, Satya, and Tushar. Most of this work was done when Arasu, Tushar, and I were at Microsoft Research. Right. So, okay, we've seen this earlier today, but what polynomial commitment schemes are. So you essentially have a transparent setup is the setting we're considering where we have no private randomness. So the prover is going to send a commitment to some polynomial f with coefficients in fp and degree at most d. The verifier asks to open f at some or evaluate f at some point z, and the prover is going to send you the evaluation y as well as a small proof pi that ensures that or convinces the verifier that the evaluation is actually correct. So what are the properties that we want? The standard completeness property is what we will ask for. And extractability is a property that we want, which says we can construct an efficient extractor that outputs a decommitment f that satisfies the correct property that we want, that is, the evaluation is correct. And the other property that we would like is the succinctness property, which says the commitment and the proof size must be small. I'm leaving small in generality here because different polynomial commitment schemes have different smallness notions, and the verifier efficiency should be sublinear in general. We can also ask hiding and zero knowledge properties, but I won't be talking about them in this talk. So what's our main result? We're going to be constructing a polynomial commitment scheme with a transparent setup, succinct commitments, in fact, constant size commitments and opening proofs. So they do not depend on the degree of the polynomial, just the security parameter. And we also have a logarithmic verifier. So the verifier runs in time log degree of f. And like Dimitri's mentioned, we also use groups of unknown order, and we use class groups this time, not RSA groups. And our proofs work at a generic group model. So one interesting fact about using these both together is we have access to this tool that's proof of knowledge of exponent from Bonet et al. Crypto something 19. And with this sort of gives us extraction for almost for free. And so I'm going to be focusing mostly on soundness, that is proving that what we extract is correct. So what are the other results that we have that I'm not going to be talking about is we have hiding and zero knowledge variants of our PCS. We're also going to be constructing constant size ZK snarks from this. We also, in a slightly unrelated news, we fix soundness proof in the dark polynomial commitment scheme, which is also in groups of unknown order. And those have also since been patched by the authors themselves, as well as block it out from Crypto 21. We, however, do incur some additional prover time, so that's unfortunate. So here's the roadmap for what this talk is going to look like. So there are two main hurdles to get over. One is the proof size. We want to get a constant proof size. And the second thing is we want verification time to be logarithmic. So I'll start by considering the slightly related notion of inner product commitments. These are very similar things. You have a vector f of length L, and the prover commits to this vector, sends a commitment C. The verifier now sends a query vector Q, and now the prover sends you Y, which is inner product of F and Q, as well as a proof pi that convinces the verifier that the inner product is correct. And ideally, we want constant proof size, and I'm putting no constraints to verifier time right now. So hopefully, it's an easier problem to solve. And note that this will imply polynomial commitment schemes directly, because we can just commit to the coefficients of F as a vector. So what's the first step? How do you commit to a polynomial or a vector? So consider your polynomial as in this coefficient representation in this form. And we'll define this int alpha of F as basically evaluate your polynomial at a large enough public value alpha. And when I say large enough, I mean larger than all the coefficients, which in this case is larger than P. So this is essentially an information theoretic encoding. You can just recover it by writing this down in base alpha, and you can just read out your coefficients again. And how you commit to this in a group of unknown order is you take a group element randomly sampled from the group, raise it to the power int alpha of F. And like Dimitri said, you have binding over integers here, and so you can commit to integers and not just modulo the order of the group, which turns out to be very useful because we're going to be working with integer equations later. So what is the intuition behind inner product that we want? So the orange term here is the term that we're looking for. That's the inner product of F and Q. And consider the product. This is the product symbol. Consider the product of int alpha of F and int alpha of reverse of Q. The reverse is sort of just important because that's how this multiplication works. So when you multiply these two, you're going to get this product. I'm writing everything in base alpha here, which is why I have these powers of alpha. And when everything is small, this will be important later. You're basically going to get the middle term here is going to be exactly equal to the inner product between F and Q. And this is the term that we precisely want. So the other terms on the left-hand side and the right-hand side, the lower and higher powers of alpha, are essentially junk. And how do we convert this to a protocol? Basically, what I written in the last slide is this. So int alpha of F times int alpha of reverse of Q. And this is something that the verifier can compute by themselves. Let's call it sigma, is equal to a bunch of terms on the left-hand side, a bunch of terms on the right-hand side, and the term in the middle that we're interested in, which is the supposed inner product. You can ignore the plus NP for now. That is just to make sure V is less than P. So what do? We put everything in exponent because we can prove integer equalities, and we're going to, what the verified check is going to be is something like C to the power sigma is equal to G to the power L times G to the power H times the middle term. And the prover sends you all the group elements that you do not need, basically the junk commitments. So the protocol looks something like this. The prover sends you a commitment, the verifier sends you a query, the prover then computes a bunch of group elements, sends it to you, and the verifier computes sigma, does a bunch of checks. So I haven't explained what the second step is here, and this is essentially a range proof, which we get using the proof of knowledge of exponent protocol, as well as Lagrange's four-square theorem. And this is the only known constant size range proof that we have. This does come with some pitfalls. We'll talk about that at the very end of the talk. So we've sort of figured out how to get a constant proof size protocol, and well, we still have some problems which I'm going to talk about. So everything I talked about before was sort of assuming that all these things are small, or when you write in base alpha, you're going to get everything correctly. But this doesn't happen in practice, especially if you have a cheating prover who can choose coefficients of F to be as large as they want to be. So what happens is when you have this equation like we had before, the middle term that we're looking for is not exactly of this form. It's going to have some overflow from the previous terms and potentially can overflow the next term as well. So how do we try to solve this? One thing what we're doing is we're going to sort of spread out F in some sense. We introduce zeros in the middle everywhere. It's basically committing to int alpha square of F, where we have a base of alpha square versus alpha. And we also have an additional check that tries to ensure that these things in the middle are actually zeros. So the cheating prover would have put, say, DIs instead of zeros. And we try to ask for an inner product with a bunch of random ZIs. And we want to ask that inner product must be zero. So the same protocol as before. The only difference now is instead of a query vector, we send a random vector. And we ask for the inner product to be zero.
So if this worked, it would all be great, but it doesn't because we don't have an inner protocol yet. That's why we are doing this. So what do we actually get? We cannot prove that DI is 0. That is something that doesn't happen. We instead get something. We prove that instead of DIs being unrestricted from 0 to alpha minus 1, we can instead restrict DIs in these weird bunch of intervals between 0 to alpha. And what these intervals actually sort of intuitively are, basically DI by alpha is very close to rationals with small denominators. So basically at small fractions from 0 to alpha, you're going to have the potential locations of DIs. And the exact form is something like this. It turns out that this actually suffices for us to extract a vector that is consistent with the inner product that the prover claims. And in more detail, how do we get this? So this is the centered term that we get in the soundness proof, which is ideally it would be just the first term, which is the inner product of D and Z. But we also get this additional overflow term that we do not like. But what this overflow term is still bounded somehow. So you can think of the equation in this format, which is summation di zi is equal to some small n modulo alpha. And what this means conceptually is a restriction on di, because you're saying that random linear combination of di's with small coefficients is also small. So this implies that there is some restriction on di that you can get. And since all the di's are independent random, you can partition the randomness space into a bunch of lines. And if the prover succeeds with enough probability, you can show that there exists at least one line with at least 2 points. And that is enough to get two equations of this form. You can subtract those two equations. They differ in only one coordinate, so you cancel out every term except di. The takeaway from this slide is basically the soundness proof relies on the fact that you have an equation like this and you can cancel out all terms except a single term, and that gives you the condition on di that you want. So well and good, we fill in the gap with zeros. Now the question is, what's the verifier time? So the verifier time in the existing protocol is linear right now, because so the verifier has to compute this term called sigma, which is essentially evaluation of a random polynomial at alpha. And evaluating a random polynomial at alpha, especially when the randomness has no structure, cannot be done better than linear time. So what is the next step to try and reduce this? You reduce the amount of randomness and structure it in some way. So one way we can do this is choose your random vector as the Kronecker product of two different vectors of length square root L. So basically each coefficient of your random vector is going to be xi times yj for random xi and yj. So this works in the sense that you can reduce the verifier's complexity with this, but your soundness argument fails miserably because we don't have those nice structure of canceling out equations anymore. So let me jump to a slightly different question now. So what is the maximum number of points in a n by n grid that do not contain a rectangle? When I say rectangle, I mean 4 corners of rectangle. And this on the right hand side is an example of a grid that doesn't contain any rectangle. So a question you can ask is, what is the maximum number of points that you can pick here that do not contain a single rectangle? Or you can, the same question in the other direction is, what's the minimum number of points you need to pick so you always find at least one rectangle? The answer turns out to be something like n root n points out of n squared. In general, for higher dimensions, you can ask the same question, but with like boxes which are 3-dimensional, like higher dimensional rectangles. And the answer turns out to be something, the best bound we know is very close to n power d. So, well, why am I talking about this? So it turns out that we cannot cancel out and isolate a single coefficient di with just 2 equations. Now we instead need 4 equations of this form, which are basically the corners of a rectangle, and we can actually subtract these in a nice way so we can isolate a single coefficient and again sort of recover our soundness proof. So the soundness proof now works if we have these 4 points that the prover is going to succeed on. But what is the probability that the prover succeeds on 4 points of this form? This is precisely the probability that there exists a rectangle in the randomness space that the prover is working with. And that turns out to give us a soundness error of 1 by square root n versus 1 by n before. So we're losing a lot just by going to square root L verification. And at higher dimension, this gets worse and worse. Eventually, this is not going to be negligible anymore if we want logarithmic verification. So this is still a barrier to log verification. So what do we do? So it turns out that these 4 points don't exactly have to be of this form. It just turns out that the difference between the 2 points must be the same. So it turns out what we need is not rectangles, but instead something like parallelograms. In higher dimensions, they look a little more wonky. So the question is now, these are more general definitely than rectangles, but how much easier are they to find? So if they're significantly easier, then we have better bound and hence better soundness. So it turns out they're significantly easier to find. And in fact, if you were looking for a rectangle, you can choose these many points so that you can't find a rectangle, but this is the maximal set of points that you can pick, so there's no parallelogram. Even a single other point you're going to add here, you're going to find a parallelogram. And this is not just a nice configuration, this is actually the maximum number that you can pick. So it turns out in general that you have a much nicer bound asymptotically compared to what boxes that rectangles and generalizations have. And this gives us significantly better verification guarantees. So it turns out that now we have we can get log verification. We just pick log L different random vectors of length 2. And each element of your query vector is now just a product of log L different elements. And now this actually gives us a soundness error of log L by n, which is a negligible soundness error, and hence we're good. So we're sort of figured out how to get constant proof size and log verification. So yeah, that's essentially what our construction is. So the main open problem we have is now prover time. So why is this an issue? So recall that the range proof I'd used long time back required this POKE protocol as well as Lagrange's 4-square theorem. It turns out that the best known solution for Lagrange's 4-square theorem, or the best known algorithm we know how to solve it, takes about quadratic time. And this is an inherent limitation of the existing algorithm. So this ends up making our prover also quadratic time. So yeah, it would be nice to have a better range proof or say better algorithms for Lagrange's 4-square theorem. But yeah, that's the talk. Thank you.
Thanks for the talk. Any questions in the house? I have one quick question. So how do you compare to schemes like Dory, which also has transparent setup?
So this is the only scheme that has a constant proof size. So with a transparent setup, we don't have other schemes that have constant proof size. So yeah, I mean, we do use the generic group model, but I think it's still interesting as we still have a transparent setup. So
Any other questions? Okay, let's thank all the speakers of this session.